Hey, can you guys hear me okay? Can you see me? It's kind of dark. I'm going to go turn some lights on. Hey, can you guys hear me okay? Can you see me? It's kind of dark. I'm going to go turn some lights on. All right. That's not really any better.
I can see you from my screen just fine.
No, it looks dark on my screen, but we'll go with it.
It's just that the whiteboard's a bit blurry, but I don't know if you can do anything about that.
Maybe that's a little better. All right. All right. So quiz is not active yet. I've got 3 more questions that I'm working on the quiz, and then I'll get that turned on. As soon. I thought I was going to get it before we started, but you guys got here early, or no, I got here late. Whatever it is, the quiz will be on right after class. I get a couple questions. I'm just tweaking that there. Then what are we talking about today? Quality and high volume manufacturing. So on Tuesday, we talked about quality and high mix manufacturing. Remember, high mix manufacturing is when the company makes a lot of different parts, and they're frequently changing between the different parts that they make. Often, that kind of a company is a job shop, so they're not the designer of the parts. Somebody else designs the parts and then says, "Hey, we need a couple hundred of these, or we need a couple thousand of these. You guys make these for us." And there's communication between the customer and the manufacturing company. When I first heard the term high mix manufacturing, though, it came from a guy who owned a company, and they owned all the designs of all their different parts, but they didn't have a steady stream of manufacturing of any single part. They made all the parts to order. And so although they owned all the designs, they were still doing high mix manufacturing. And today I want to talk more about high volume manufacturing, which really isn't something that we see a lot of now. We don't see any of it here at WPI. In the WPI manufacturing labs, we're always going to be acting like a high mix manufacturing company or high mix manufacturing or making place. I guess we don't sell a lot of the stuff we make here, so we're making stuff, we're not manufacturing it, but it's the same physical processes, right? So, but I'm assuming that since nobody's sat down that I saw when I asked the question about trust funds, I'm assuming that we all want to have jobs sometime, and that many of us are going to end up working at companies that actually do high volume manufacturing. So we should at least talk about it. And when traditional manufacturing engineering textbooks talk about quality in manufacturing, they almost only talk about the topics that are important to big companies. And I think this is probably a problem with textbooks in general, is that they often focus on big established companies, big established problems. Business textbooks are the same way. But anyway, so that's what we're going to be talking about today. What does it mean to do high volume manufacturing? Is anybody, we talked about the difference between high mix and high volume manufacturing on Tuesdays. Anybody remember what we said the high volume manufacturing stuff was?
It was the or a high volume or high mix,
or the difference between the two.
The high mix was it wasn't always the same part. Like it would be like a second or third tier company.
Sure. And the high volume manufacturer may also be a second or third tier company, but they're always making the same parts on the same machines. They very infrequently change a machine from one part to another part. There's a company that, what town are they in? They're in one of the towns right around Worcester here, that we worked with a couple years ago on an MQP. And in their process, in their machine shop, they had 7 identical CNC milling machines, all of them running 24 hours a day, 7 days a week, all of them making the same part. That is high volume manufacturing. If they could have made the parts faster, they would have made the parts faster. In that process, they knew that they could sell the parts faster than they could make the parts. And so those machines never got changed over to new parts. That's clearly high volume manufacturing. And the MQP did a lot of stuff to help them figure out that process better so that they could reduce the cost. They weren't making more money, but they were reducing their cost so their profit could go up on those parts. Anyway, so we talked about quality on Tuesday. Somebody other than Sam, tell me what is quality in manufacturing overall?
You do for quality, you deliver to the customer what they need when they need it.
So quality in manufacturing across the board is delivering to the customer what they need when they need it. Okay, now what about quality control? So you could get a job out of WPI as a quality control engineer or as a quality assurance engineer. I'm going to say those two things are the same thing. You could become the quality manager at a company. Again, it's the same idea. What is this idea of quality control? Intuitively, what does that say to you? What does that mean to you?
You're making sure all your products are consistent and to the same quality.
So it's to make sure that everything we make is consistent and of the same quality, and that quality should be the thing that the customer wants, right? And so if someone else designs the parts, then they give us these design specifications, and there's tolerances, and the design specifications include things like the geometry of the parts and the surface finish, and maybe if it gets paint on it, things like that. And so we talked about that on Tuesday or maybe on last Thursday. So that is if we have someone else designing the parts. If we design the parts ourselves because we are the manufacturer and we're the seller of the parts, then we still want to make those kind of design specifications, because typically the designer and the person doing the manufacturing. I just saw somebody was typing in the chat. Oh, there it is. Okay.
I was just
I'll
asking.
get the chat window open too.
Yeah, I was just asking, like, for the high volume, since it's the same part over and over and over again, would you have like robotics, like an arm or something that would just like put in the blank, take out the part?
Sometimes. The guy who taught me the term high mix manufacturing, because I was just called that job shop type of manufacturing in my mind. So he owns this company that makes components for brakes on motorcycles. There are a lot of different motorcycle brands out there. There are a lot of different motorcycle models out there. They make aftermarket parts for all these different motorcycles. It's basically the same part, but they're slightly different from each thing. He wanted to buy a robotic system to automate that process you're talking about. So the loading of the parts and the things like that. But because all of his parts were different, it would cost him for each part family about $100,000 to integrate that with a robot, which it doesn't sound that bad, but then every time you change the design, you had to modify his robot. So he actually created a fixturing system that the robots could use. And so now he has 2 companies. Now he has a robotics manufacturing company where he makes robotic systems for high changeover parts, and he makes brake parts for motorcycles. So yeah, a lot of times you want to go there, especially if your company is located in a place where labor is expensive, like China. I don't know if you know this, but the cost of labor is going up in China, and Chinese manufacturers are doing tons and tons of automation with robotic systems. So, all right. So, what was I saying before I saw the little chat thing flash and it distracted me? Did you know that humans, we used to have about a 20-minute attention span? They documented this back in like the 1950s. Do you know what the average attention span of an adult in the United States is today?
8 minutes.
No,
Probably 5 seconds.
3.
7 seconds is the last data I saw. It's because of these devices that we always have in our hands. 7-second attention span. My data comes from studying marketing. So if I want to get you to pay attention to my marketing message, I have to capture you in the first 7 seconds. So it may be skewed. Probably college students in class with their camera turned on have a slightly longer attention span, but I'm not sure about you guys that don't have the camera on. I'm not even sure you're real people. You know, anyway, we won't talk about Zoom lectures. I actually really like some parts of the Zoom lecture. I like the part where when you talk, I can hear you. Whereas that's not always true in the classroom. Certainly it's not true that everybody else can hear you when you talk in the classroom. But anyway, what was I about to say when I got distracted? Anybody remember?
I think you were talking about quality control with manufacturers that are
Quality control. Okay. So the question was, what is quality control in a large volume manufacturing company? And so we saw on Tuesday that if we do inspection, if we do a quality inspection, we can make sure that we don't ship crap to the customers. Right? So if we do inspection, we can make sure we don't ship things the customers don't want to pay for. And we can do that inspection in steps along the way. Or we could do that inspection just before we put it in the box to ship it to the customer. And so if we do it in steps along the way, so if our part has several processes that have to happen to it before it's finished, if at the end of each process, we make sure that we don't do the next process on any parts that weren't correct out of this process, then it makes it easier for us to not make crap, or at least we stop sooner. So one of the things we're trying to do, especially with our in-process quality control, or in-process quality control, which means when you do when you do an operation on a part, you check to make sure you did it correctly. And then you flip the part over, you do the next operation on the part, you check to make sure you did it correctly. If you do that, then when you find a mistake, you can correct it immediately. If you're waiting until you get to the end of the process, so if anybody's ever bought a television, one of the things you like to be able to do when you take the television out of the box is press the button and have it turn on after you plugged it into the wall. But there's thousands of components inside that television, probably on the boards and things in the computer part of the television. If all they ever did was assemble their televisions, right before they put it in the box, they turned it on to make sure that it turned on, they could make sure that they didn't ship any bad parts, any bad televisions to the store, which then got to you. But it wouldn't be a very good way to run the company if, when they were making one of the circuit boards in there, they had a mistake on it, and they assembled all the televisions, only to find out they don't turn on. They don't even know which part is broken when the television doesn't turn on, right? So in-process quality control has the operator of the machine tool, often if it's a machine part, the operator of the machine tool, when the part comes out of the machine, they'll measure it to say, oh, yeah, that's the diameter, it's within tolerance. And you've got to have, here, Here's some M1800 parts. So in the lab, once we get in here, you'll be making components for a thermoacoustic engine. Here's a cylinder. Here's a piston. The piston has to be able to fit in the cylinder. And if I plug up the end, it shouldn't fall out until I let the air in, right? So it's got to be a close enough fit so that air can't get past it from the force of gravity here. That one's probably not going to be a good fit anymore now that it dropped on the floor. So if it's too small, the piston will just slide out, and in operation, the air would just rush past it. It wouldn't operate. If it's too big, it won't fit in the cylinder, right? So when we're making these cylinders, every time they come off the machine, we want to see what's the inside diameter of the cylinder. We actually need to know what there's some grooves on here. We need to know the depth of those grooves. And so there's some things that we can measure for each part as it comes off the machine to make sure that the part is good before we ship it to the customer. In your case, before you put it in your little box of parts. So, and if we measure each part, and we measure these critical dimensions on each part as it comes off the machine, we're doing 100% inspection. Does that make sense? We measure 100% of the parts, we do 100% inspection. Do we need to do 100% inspection?
Sometimes. Depends on what you're making.
Okay. Give me an example of something
Ideally,
you
no.
want to do 100% inspection on.
Like you,
Something, sometime when it's critical that the part needs to work every single time. Like when the consequences of the part not working, when people die.
Okay. So
like
if the part fails and people die because of it, that's a good time to do 100% inspection.
Yes.
Yes. When else might you want to do 100% inspection?
if it's a really expensive part, like
If it's a really expensive part, I don't know that necessarily puts it over the top for the need for 100% inspection.
Okay.
If the part is a part of a complex assembly that is hard to get to, maybe.
So if repair or something is going to be very difficult in the future,
Right.
that might be a good reason to do it. Why wouldn't you want to do 100% inspection?
It's
Takes
expensive.
a lot of time.
Because it adds
time
cost
is money.
to the part.
Cost
So you
and
never
time.
want to do 100% inspection if you don't have to, because it adds cost without adding value. So if the inspection adds value, you want to do it, right? So in our manufacturing company, one of the things that we manufacture parts out of hard to machine materials. We machine a lot of ceramics and things like that. Very difficult to machine materials. Sometimes the tool wears out faster than the workpiece material wears out. So if your process is very difficult to control, you need to either do a higher sampling rate. And so sampling is when you measure like every 10th part or every 100th part or every 1,000th part, right? So you either need to have a higher sampling rate or even get to 100% inspection if you have a process that's very difficult to control. So if you have a process, go ahead.
I don't think I agree that 100% inspection adds no value, because if you take into account company reputation, that is, I guess it's more of a business type value.
It
But
could add goodwill, which is value to the
Right.
company, but not value to the part.
oh,
I agree
okay.
with that.
Okay.
And if you've got good marketing people, they'll talk about the fact that you do 100% inspection. If you've got engineers as consumers, they'll think, well, they're wasting money if they're doing 100% inspection. But I think, so never shipping bad parts to the customer will give you as much goodwill as 100% inspection. You only do 100% inspection when you have to, in order to not ship bad parts to the customer. Or like somebody said, if the risk of the part failing is extreme. So if the risk of failure in operation is extreme, like somebody will die, like the car engine will explode. So if the risk is extreme, then the cost of doing the extra inspection is insignificant. But in general, you want to do as little inspection as possible. You just want to never make bad parts. If your process is fully in control and it does not make bad parts, you don't need to measure the parts. All right, so let me see.
Would you also want to do 100% inspection when you're first setting up a manufacturing line?
So you're going to do more inspection on the first article. So
Okay.
Making the first part,
Yeah, that's what I was just
have more inspection for just that reason. You haven't yet established a controlled process. We had that's a story for a different day, but I've got a story where, yeah, story for a different day. It's when we get to the design issues. So I think I'm still sharing the screen, right? So
Yeah.
This is our second or third $100 bill in the class, right?
Second.
Have you ever studied the back of a $100 bill?
Which one?
Doesn't matter.
Yes.
Yeah.
Studied it, right? It says right there on the top, it says, "In God we trust." Have you ever zoomed in on that? Like put it under a microscope, see if there's a subtext? Everybody else bring data. So we need to, if we're going to control our manufacturing process, so it's great to measure the parts when they come off the machine, right? And say that's a good part, and you put it in the box with the good parts. But if we just do that, we lose a significant amount of information about our manufacturing process. I think I'm going to turn off the screen share for just a second here. And now I want it to be so that view here, speaker view. And I want you to see me, right? Okay. And when you see me, I want it to be, all right. Anyway, I think this is going to work. You can see me and you can see the whiteboard.
Yeah.
I wrote on the whiteboard last time we were talking. Yeah, somewhere there's a whiteboard marker. Can you read this blue?
Yep.
All right, perfect. All right, so if we measure our part as it comes off the machine, and on this part, there's actually a couple of critical dimensions. The diameter of the cylinder is a critical dimension that we want to control. And so we can measure that diameter as it comes off the machine. The other critical dimension here, because when we assemble these, there's a test tube that slides over this end. And it's held in place. We put two O-rings in these little grooves. And so when you slide the test tube over it, if this piece is too big, the test tube doesn't fit. If the grooves are not deep enough, you have to push really hard to get the test tube on and it shatters and you get a piece of glass in your hand and you have to go to the hospital. So there are some critical dimensions that we've learned these things empirically. We've only sent one M1800 student to the hospital with glass in his hand.
Many others to the hospital, though.
But after that, we put gloves there. So we required gloves also for the pushing on. So two fixes, but the really important fix, we never broke another test tube that way after we started controlling the depth of the grooves, right? So we had to measure these. And if we just say, all right, it's either a good part or a bad part, and we throw it in the bin with either good parts or bad parts. The ones that are bad parts, what do we call those? Anybody know?
Rejects.
You might call them rejects if you're speaking in polite company, but what do we typically call them?
Defects.
Well, they have defects. That's why we call them scrap.
Junk.
So I call them crap, but the technical term is scrap. And so when we scrap a part, we throw it away. It's not valuable anymore. So we could keep from shipping bad parts to our customers by measuring the parts, the critical dimensions, put the good ones in the box to ship to the customer, throw the bad ones in the box as scrap. If we want to actually learn more about our process, we can make a graph. You guys can see that?
Yes.
Black marker, I think, works better. I don't know where the black marker is, though. It's got to be one here somewhere. All right. So let's say, if we're measuring the inside diameter, which is what makes the part function, I'm just using this one because I know what the nominal dimension is supposed to be. It's supposed to be 0.860 inches. So I know that my parts are supposed to be 0. So we'll make our chart here with hopefully our mean line is represented by this line. And we start making parts. And so we'll have, you can see the dots.
Yep.
Okay. So if we make our chart and it looks like this, it won't be quite as even as every other part above and below. But if we make a chart and it looks like that, what do we know about the process?
It's good, but it's not quite there.
Well, this
In control.
It's
depends. You don't have a scale on the chart, so you really don't know, right?
it's
If this
accurate.
is 0.8605, so 5/10,000ths of an inch bigger. And so this would be 0.8595. So this, if this is what I saw, and we were plus or minus 5/10,000ths of an inch on our scale, I would be thinking this is phenomenal, right? So you guys, somebody who's on their computer, Google, what's the thickness of a human hair? I forget the number. Maybe I should have asked.
0.04 to 0.06 millimeters.
Somebody convert that to inches, so we can all use the same units.
Anywhere from 1/1500th to 1/500th of an inch.
500. So how many zeros then?
2, or wait, 3 for the 1/500.
3 zeros and a 5 out here. I don't think it's that small.
2 zeros and a 5.
2 zeros and a 5. Okay. So this difference then is 10 times smaller than the thickness of a human hair. So that would be a really controlled process. The other thing I see about it is that this up down that we're getting around the line is staying the same. and it's along this mean line, which is our nominal value. What if we make a graph that does that? What do we know about the process?
There's something wrong.
Something's wearing down, or something's going wrong that's making it like get less and
So
less.
the diameter seems to be growing. Actually, on an internal diameter part, it probably would normally go the other direction. But we'll leave that. The diameter is growing. What could cause the diameter of the part to grow over time? The inside diameter of our part. What could cause that to grow over time?
Wear, like wear and tear.
Wear on the tool would probably make the inside diameter get smaller over time.
Could it be heat?
Heat.
The cutting head gets worn down.
As you operate the machine over time, it warms up. As you operate a machine over time, it warms up. As it warms up, some of the components get bigger. Especially the metal components, they tend to get bigger as it warms up over time. And so if you see something like that, and then it levels off, that's probably caused by growth of some component in the machine tool from heat. Does it matter?
No.
Now, would that depend on the tolerance of the part?
Exactly. If the tolerance is way up here,
Like if it allows for it.
there, it doesn't matter. If the tolerance is here, then all these parts over here are scrap. So it 100% depends on the tolerance of the machine, or so the tolerance of the part. Now, if we knew it was going to do that, what could we do?
Add more coolant.
It's not, so what the coolant does is it takes heat away from the chips, and it takes heat away from the workpiece. But what causes a growth like that is actually when the spindle warms up and the spindle changes size. So when the machine tool itself changes shape because of heat is what could cause something like that. And it's typically, those kind of growths are typically in this 1,000th of an inch size. I had a part where one operation on the program lasted 24 hours. In the course of that 24 hours, if we started that program with a cold machine tool, the spindle would grow 1,000th of an inch over that time.
Wouldn't that also depend on the material that you're using? Because like aluminum would be like cooler than titanium or something.
So it actually, so this kind of growth we're talking about here is the machine growing. So it depends on the material the machine's made out of. Yes.
Okay.
The part growing, and these brass parts, we actually used to measure that in 1800. We would measure the diameter when it came off the machine. Then we would put it in a bucket of cold water and measure it 10 minutes later. And it would be about 2,000 smaller 10 minutes later after being in cold water. So this brass part actually changes a lot with heat. So the temperature at which you make a measurement impacts greatly on your ability to control the process too. So if you see it trending up like that on an inside diameter part, if it's trending up like that on an outside diameter part and it continues to trend up, that's going to tell you that the tool's wearing out. And you want to change the tool, or you want to adjust the tool offset to bring it back down. So one of the things we do as we're making our parts is we'll make what we call a control chart. And so we've got a nominal value here that we want to make the parts. We'll have some upper control limit here. We creatively call that upper control limit the upper control limit, or UCL, and a lower control limit down here, which again, as engineers, we call the LCL.
Can you put the label above the LCL? Thank you.
And as we're making our parts, if we get variation here, and it stays in the middle, then we know we're making good parts and we're good. Now, we could be, so each one of these data points on our graph could be every 1,000th part. Doesn't have to mean we measure every part, but we need to figure out our sampling interval, and then we measure those parts along there. If we do that, we can know if our process is in control. If we get a piece that comes outside the upper control limit or the lower control limit, now, these upper control limits and lower control limits, we don't use the tolerance. We use so we want the tolerances to be outside of that, so that when we take action to control the process, we do it before we've made a bad part. Does that make sense? All right. So this is a control chart. Now, everybody here knows how to calculate the mean value, right? Right. I think we got that in what, 3rd grade? And as people who are good at math, you still remember how to do the math you learned in 3rd grade. Have you ever tried to teach somebody something that you're really good at and that they don't understand it?
I had to homeschool my brother in algebra.
Yeah, I was, after our class yesterday, I was helping my my daughter with algebra. And I kept wanting to step back. I said, well, at what point do you not understand this? So let's just talk about the stuff you needed to understand before. Yeah. After my wife got home from work, she took over. Apparently, my wife's better at teaching math than I am. I think it's really that my daughter screams at her less. All right, you guys know how to calculate the mean. What about a standard deviation? I know how to calculate standard deviation.
Is this relative?
Go to Excel and you type equals STDDEV, open parentheses, you put the thing and then you close the parentheses, right? And it tells
Yes.
you, that's how I calculate a standard deviation. I've got a textbook here that shows the formula. And yeah, there's a formula for it. What is the standard deviation though?
Isn't it like the standard like error or something, like the
quick way to think of it is the average the average distance of the points from the mean value. So the average distance of each point from the mean value is the quick way to think about what that standard deviation is. So if you've got a huge range and your points fill that huge range, then you're gonna have a high standard deviation. If you've got, you could have a huge range, but only a few points are at the extremes, you'll still have a small standard deviation, but it's the average, basically it's the average deviation from the mean. Okay. If we plot, this pen really doesn't work well. Hopefully this one works better. So if we plot this way, where this is our mean, the mean value that we want, and we just look at how many of our measurements how are our measurements distributed around here, disregarding the time or the number of measurements, right? So it's just the number of measurements. So if we have a bunch of measurements here, like this, if we just plot here. We need to fill it in. So this is the distribution of our measurements around the mean value. And we'll have our lower control limit and our upper control limit here. And so when I drew the line, when I drew the points that were all within that, the control chart, it would have given us a distribution something like this for the distance to the mean line. If the mean line was down here somewhere, but we're still within the upper and lower control limits, what we're saying is we're making the parts on average a little bit too big, but not so much too big that they're not good parts. So a little bit bigger than the nominal value, but not so much bigger that they're not good parts. Now, let's go back to where we're centered on the mean. So if the parts are coming out a little bit too big on average, what can we do to fix that at the machine tool?
Compensate in the G code?
We could compensate so we could change the program to make the parts a little bit smaller. We could actually, and you'll get to this later in the class, but there's actually some other things that we could do where we just, without editing the program at all, we can just make some changes on the controller and it will make those adjustments automatically for you because of the CNC part, because of the computer part in the CNC. You can do that. So if you're off by an offset, you can almost always correct that. What if, though, our control limits, let's see if I do a different color, are like this compared to the parts we're making? What do you know about this process if this is our distribution of parts and here's where the control limits are?
Making a lot of crap.
What we know is all these parts here are scrap. Is it possible that the process is in control still, though?
Yes.
What this would tell me is that the process is in control, but the machine's not capable of making the parts all in tolerance. Can you still use that machine to make these parts?
Yes.
You just have to do more inspection. And you have to be willing to scrap the ones that are too small and maybe rework the ones that are too big. So one way you fix scrap is by doing what we call rework, which is putting the part back in the machine and operating on it again. All right. So, all right. Who's heard the term Six Sigma?
Yeah, actually, I did a bit of reading on it during the break.
Term Six Sigma. Did you know you can get a black belt as a Six Sigma? And I don't think you have to punch anybody in the face to get it. Although, if you go to the Six Sigma training, you might want to punch the trainer in the face more than once during the training. I know some people that do Six Sigma training. I should ask them if anybody's ever punched them in the face. All right, so when we hear Six Sigma, and this is, so you could spend, I don't know, probably $10,000 to take special training classes, or you can, there's a class that's offered by continuing education here at WPI to become a Six Sigma black belt. So you can take that. It costs several $1,000s, I think, to take that class. There's no black belt certification class as an undergraduate, but there are plenty of classes in school of business where they talk about this. So you could learn it, but I don't think you can get certified. what the Six Sigma is where what we want to do is we want these control limits. And this is my brief, quick discussion of it. I can post links to videos that describe it in detail for you. What we'd like is for this to be 3 sigma here and 3 sigma here. So the distance between the control lines is 6 sigma, whereas sigma is the standard deviation of the data set. And if we can make a graph like this, where we're making parts, what's the best way to explain it? So remember, these upper and lower control limits are based on the tolerances for the part. So if our machine is able to make parts with very low variation, then we can get within plus or minus 3 sigma. Or if we can have very large tolerances for our part, we can get between plus or minus 3 sigma, which is why the Kia costs $20,000 brand new off the line, and the Mercedes-Benz cost $150,000 brand new right off the line, because the parts in the Mercedes-Benz have tighter tolerances, which is why we feel like the Mercedes has higher quality. Now, we realize that because of the definition of quality, it depends on who the customer is. But Mercedes has to buy more expensive machine tools in order to make their parts, because their parts have tighter tolerances. Kia can buy cheaper machine tools, which makes the cost of manufacturing the car cheaper. Both of them can make most of their parts good. Bigger tolerances can give you easier manufacturing, can let you make parts cheaper. Tighter tolerances can give you more precision, which might allow you to do things you can't do with big tolerances. So I think we're almost exactly out of time. And I think that's a good place to end here. I am going to put links to a couple of websites and to another video that describes determining your machine tool's capability, and it describes doing some calculations using those upper and lower control limits and calculating what we call a CPK and a PPK. And the CPK and PPK, they're just a measure of the ability for that machine to make that part with those tolerances. And so I'll put that up there. Give me 25 minutes. I'll have the quiz live for you. And also, I'm updating the Canvas site throughout the afternoon. There'll be links to all the lecture notes. There'll be links to the recordings of all of the lectures, except yesterday we forgot to click record, so there's no recording for yesterday. Oops. I'll see if I can put a link to sometime when I talk about similar stuff as yesterday. And I'll stay on. I'll go ahead and stop the recording, then I'll stay on for any questions.
How long is the quiz available for?
It'll stay available forever. It's due on Friday at midnight.